All right, let's continue our discussion on Simon's problem and this algorithm. So just to remind you, in Simon's algorithm, Simon's problem, we have a black box function which hides a string S in the sense that two inputs get the same value if only if the two inputs are shifted by the secret string S. So our goal is to find S. Okay, and then here's the quantum algorithm due to Simon. And the critical piece is this sampling procedure, which we've designed this circuit with everybody's help. So let's kind of see what this sampling subroutine does. Okay, and let me just write down some useful algebraic identity without proof. So if you apply Hadamard on the n-base string, on each one of them, this gives us another state which looks a little complicated, but really not too bad. So it's going to be a superposition over all n-base string with a sign in front of it. And this sign is determined by the dot product between x and y. Okay, so just to be clear, x dot y is x1, y1, xr, x2, y2, xn, yn. So it's going to be either 1 or 0, which determines the sign in front of each y. And in particular, the special case here is if you apply Hadamard to the all 0 basis state, this gives us a uniform superposition over all strings. So this is going to be let me put in the normalization factor here. Okay, so this is just a little identity which might be useful. So now we look at this sampling subroutine. And just as before, we can follow the circuit and figure out the states at each stage of this circuit. And I'm going to skip this calculation for the first few steps, but just directly tell you what the states will be at this point. Okay? And I believe you will be able to derive it from this identity I just showed you. So the state of the entire system here will be 1 over 2 to the n, sum over x, sum over y, and then ket y, ket f of x, and then with the phase here, -1 to the x dot y. So that's the state and this point. Okay, so we're going to measure this top n qubit, and this is a new operation we didn't, explicitly talk about before. So we're not measuring the entire 2n qubits, we're just measuring part of it. This is called a partial measurement, but it follows, the rule you would expect. So the probability, so we're going to observe some outcome y with certain probability. So the probability will be proportional to the norm squared of what's in front of y. So we have 1 over 2 to the n, summation x, and then -1 to the xy, and also this f of x register here. So this is a vector, right? You take the 2 norm, and that's going to be the probability of seeing this outcome y. Okay, so let me do a little bit of simplification. This is going to be, so what I'm going to do is to think of the premise of this function. This function, it has, for any function value, there are exactly 2 inputs given to that function value. So I'm going to sum this, instead of over the input strings, I'm going to sum over the range of the function f. So for each possible function value z, I have some coefficient here, alpha z. So let me write down this alpha z down here. So again, there are just going to be two terms corresponding to this function value z. Let me call one of them x. God, what's going on? Somebody want to listen to this lecture as well, I suppose. Okay, so there are going to be two terms here. I call one of the input xz, and then from the promise of this function, we know the other input, which is going to be xz XOR with s. Right? These are the two inputs get mapped to the function value z. Okay, so let me pull out xz times y, and we are left with 1 plus -1 s times y, s dot y. Okay, now something interesting is happening. What is this sum I just highlighted? If y dot s is 1, what do we get? We get 0, right? Because this introduces a negative sign, so 1 minus 1, they cancel. But if y dot s is 0, then they will add up. So this is not going to be 0. And in fact, we can show for any y, this is going to, let me just write not 0 for now. And from here, we can derive that the probability of observing a string y is going to be 0 if y dot s is 1. And then for any y, it's going to be non-zero, and in fact, it's going to be the same for each y. So it's going to be 1 over 2 to the n minus 1 if y dot s is 0. So this is what the sampling procedure tells us. It's sampling from a distribution where it's uniform over the strings that are, I call it orthogonal to s. So let me show you this geometric interpretation. Imagine this is our secret string s. Okay, and I consider this orthogonal hyperplane. Then this sampling procedure basically is sampling uniformly from this hyperplane. So let me call this S-perp. So S-perp is all the strings with 0 dot product with S. And then this quantum subroutine samples uniformly from S-perp. And then you can imagine with enough samples from this hyperplane, we can reconstruct S-perp and then from there figure out S. And in this particular case, this just involves solving a system of linear equations. So we can, again, we can reconstruct S-perp and then compute S. So basically, all we need to do is to, get n-1 linearly independent samples in this hyperplane. And that, take linear many samples will be enough. So this is I think this actually finishes the analysis of Simon's algorithm. Again, let me just emphasize, the key here is when we run this sampling subroutine, we're sampling from a really nice distribution. From there we can recover S. So this gives us a quantum algorithm that solves Simon's problem with linear many samples. So let's just compare. As we said earlier, a deterministic algorithm will take 2 to the n minus 1 plus 1 queries. And then a randomized algorithm, we need to find the collision, which is going still needs square root 2 to the n. And this quantum algorithm, big O of n, so exponential speed up. Okay, any questions? All right, if not, we'll move on to the next problem or algorithm. So Simon's algorithm is going to be a precursor or the inspiration for the factoring, the famous factoring algorithm. And in fact, it turns out Simon's algorithm can also be used to break some crypto systems. And in fact, symmetric crypto system, which is kind of surprising. And you'll see some exercise in the TE session this afternoon. Okay, so let's move on to the discussion on the famous quantum factoring algorithm. So my original plan was to, tell a really nice story, the full story, which starts with phase estimation, which will introduce this important quantum Fourier transform, and from there we can go to order finding and factoring. I mean, I like it, but then I realized for this summer school, maybe this is not necessary. So I'm going to just jump into this important unitary operation, which is called quantum Fourier transform, and from there, build on the factoring algorithm. So let me go here. So let me directly introduce this unitary transformation, which is arguably one of the most important unitaries in quantum computing. So consider a computational basis state, which I denote as ket j. It ranges from 1 to 2 to the m minus 1. Let me use capital M to denote 2 to the little m. Okay, and then let me define another set of states. For each j, I define phi j, which is going to be 1 over square root 2 to the m, summation over k, omega m, j times k, and ket k. So this omega m is just the m root of unity, so e to the 2 pi I over m. For those who are seeing this for the first time, on the right-hand side, this might look, really ugly. But in fact, we can verify this set of vectors, they are orthonormal to each other. That means they form a basis for this m-qubit space. So on the left-hand side, we have the standard basis, the computational basis. On the right-hand side, this is actually the Fourier basis.
I'm sorry, here by J dot K, you mean something different than what you said before? It's no longer the XOR?
Oh, exactly. I'll clarify in a moment. Here, J times K, that's multiplication mod M. Okay, you treat J and K as integers, multiply them, and then modulo M. Yeah, very good question. So since these are two sets of bases, there's a linear transformation, and that's the transformation we're looking for. I call it F sub M. So in matrix form, it's a linear transformation. We can write it as a matrix. When I write down the matrix, I think many of you will recognize maybe under some different names. So this is the metric form for this linear transformation. suppose you might have seen this in your algorithm class, because as a linear transformation, this is known as discrete Fourier transform. And in a standard algorithm class, you've seen, the fast Fourier transform algorithm to compute this. So we have the FFT algorithm. So we know the FFT algorithm runs in time. Does anybody recall? The fast Fourier transform algorithm? Anyone? Okay, I guess I'll just show you this, and you can tell me if you agree. So it scales with, m log m. And then in the quantum setting, there is actually a quantum circuit for computing this transform. And that quantum circuit is what we call, abusing the notation, we call it quantum Fourier transform. If I wish, I use a subscript M here as well. And the quantum Fourier transform circuit, actually has complexity big O of polylog in M. As you can see, there is already an exponential improvement. But I should remark that, in the fast Fourier transform algorithm versus the quantum Fourier transform, they're not exactly computing the same thing. In fast Fourier transform, we're given a vector and then we compute a full vector, meaning we have the entry, each entry in this vector. But in the quantum Fourier transform, we have this vector encoded in this quantum circuit as amplitude, and then we can transform that state into a new state where the amplitude will correspond to the Fourier transform the vector. Okay, this is distinction. But this exponential improvement is still really significant for designing quantum algorithms. So let's keep this transform in mind. You don't have to, I didn't introduce that, and you don't have to know how to actually implement this circuit. It's going to be, this is the complex, but we just need to know there is such a transformation which can be done efficiently, really efficient. Okay, so with this, I can jump to the most influential quantum algorithm, if you wish, the quantum factoring algorithm. Okay. So just to define the problem clearly so we can be on the same page. What is factorization? Everybody knows that, I guess. We're given a big integer which is the product of two primes. And the goal is to find the prime factors. Let's say I just find this p. Okay. So here, I should say the complexity will be measured in terms of n, little n, the input size, which is log of the number, the integer number n. So this is the input size, input length. And this is considered a very hard problem classically, right? So the best classical algorithm is based on number field C if it runs sub-exponential time in little n. And we'll see there is a quantum algorithm that can factor in time poly in n. So here's the outline. So you want to solve factoring. So it actually can be reduced to another problem called order finding. And this step is purely classical. And this is well known in number theorists. And then from order finding, to solve order finding, we have a quantum, we have a quantum algorithm which uses quantum Fourier transform as a key component. So this root is actually, the original Shor's algorithm. And there's another approach, which is what I indicated earlier, based on Kitaev's phase estimation technique. We won't be able to talk about this, but for those who are interested, there's reading material on this. It's equally, if not more, insightful as Shor's algorithm. So we will go through Shor's path, okay? So let me introduce what this intermediate problem is, order finding. So consider a number which is co-prime with n. So we denote this Zn star. These are all the numbers. Co-prime to n meaning the greatest common divisor is 1 with n. So the order of A mod n is going to be the minimum exponent you can raise A such that you get 1 mod n. So this minimum R is called the order of A. Okay? And then the order finding problem is to say, given a modulus n and the number A, the integer A, we want to find the order of A mod n. Okay, is this problem clear? Good, good. All right, so again, as I said, classically, and number theorists have known this, factoring reduces to order finding, and in fact, they're equivalent. If you can solve one, you can solve the other. So we won't be going through this proof. Now, given this, we will be focusing on solving order finding. And let me introduce another operation which will be critical, and that is modular exponentiation. I suppose John, you covered this kind of in the lecture yesterday? No? Oh, okay. Then let me introduce this modular explanation very quickly. So basically, we will consider a function which is parameterized by this number A. It takes an integer and maps to another integer, but I'm just going to say a set S. Okay, and suppose the order of A is R, just for shorthand notation. And then this function E sub A is going to take an integer x and then raise to the x power mod n. So you just multiply A x times and modulo n every time. So what's interesting about this function is that, think about it. When will two inputs give you the same function value? This happens if and only if the difference between xr is a multiple of r. Right? Because a to the r is 1 modulo n. So you can just add multiples of r to your x, and you get the same value. So this is a critical observation. And then this modular explanation can be computed efficiently, and we can turn that into an efficient quantum circuit as well. So we're going to treat this as a unitary implementation of the function EA. So we have ket x, ket y, and it will give us ket x, and then computing a to the x mod n to the output register. So this can be implemented efficiently. Okay, now we can see Shor's order finding algorithm. And this algorithm, if I, once I draw the circuit, it proceeds pretty much the same as we've seen so far. Right? So I'm going to initialize m qubits on the top and n qubits on the bottom. So I'm going to use slash to represent our multiple qubits. So same old stuff, doing Hadamard on the top m qubits. And then followed by evaluating this function, E sub a, the modular exponentiation. All right, now here's the question for you. What should we do next on the top m qubits? Well, we just spent a few minutes talking about a unitary. Do you recall? The quantum Fourier transform, right? That's what we will need here. And after that, we measure, get some classical string. So again, this is going to be repeated a few times. And from this classical samples, we can compute R by a classical algorithm called continued fraction. Okay, so I want you to analyze this algorithm on your own, and you might be wondering, what the heck is going on here in this algorithm? I'm going to show you some intuitions in a moment without the formal analysis. But you might have already observed there is a common pattern in all the algorithms and the problems we've described so far. And in fact, there is a very nice algorithmic framework that unifies all the problems we've talked about so far. And I'll spend a little while to explain that framework. So this is known, question? No? Okay. So this is known as the hidden subgroup problem. And sometimes it's also called period fighting when it's applicable. So this is going to be a general family of problems, and we'll see special instantiations which will subsume the few examples we've shown. Okay, so in this hidden subgroup problem, or HSP in short, we have a group G and some set S, and then we're given a black box function f from G to the set S. And the promise of this function is that it hides some subgroup, meaning there is a subgroup H such that for any two group elements, their function values will be equal if only if they're in the same coset. So let me break up this condition. So this means, on the one hand, this function is periodic. Namely, for any group element and any element in the subgroup H, if I shift x by this subgroup element, I get the same function value. Okay, this is what I mean by periodic. And the other condition is it's injective across different cosets. That means if x and y, they are not in the same coset, then they have distinct function values. Okay, so pictorially, we can kind of partition the group G into cosets of H. So here's H, here's G1, the coset G1. And then each coset will be mapped to the same function value. So I'm going to use some symbol to represent. But across different cosets, the function values will be distinct. So the different symbols represent different function values. So the function has this property. Right? It hides the subgroup H in this way. And the goal here is to find H. So this is the general framework of hidden subgroup problem. In this general form, it looks very abstract. But we will see that actually the examples we've shown can be fit into this framework. Okay. Before we get there, any questions about this general definition? Okay, so let's see how this framework actually subsumes the examples we've discussed so far. So I'm going to create a table here. So to specify the group G and the subgroup H in each case. Okay, so in Deutsch problem, the group is actually just Z2, 0, 1, under the XOR operation. And the subgroup in Deutsch problem is either 0 itself or the entire group G. Right? So this the 0 case corresponds to a balanced function. And the subgroup in G means the function was constant. And then Simon's problem. The group is just the hypercube Z2 to the n under XOR. Okay, so can somebody identify what would be the subgroup in this case, the hidden subgroup in this case? It's 0 and S, exactly. Right? And then we can have all the cosets, which are shifts of 0 and S by another string. And for each coset, the function values are the same, and they have distinct values across different cosets. So we can see Simon's problem is also a special case. All right, now coming to factoring, or rather, order finding. What's the underlying group? Let me show you the function we've worked with before. Look at here. So the underlying group is actually Z, the integers. And we are using just regular addition as the group operation. Now the interesting thing is, what is the hidden subgroup in this case? What's hidden by the modulo exponentiation function? Let me give you another hint. The property we observed earlier. So what's the hidden subgroup here? Somebody will realize when I write it down. Multiples of R, the order of A. Okay. So these are the examples we've discussed, but there are more. For example, in the very paper, Peter Shor also gave a quantum algorithm for discrete log, and that can be seen as a hidden subgroup problem on the set on the group Zn cross Zn. And then there's further generalizations. So there's a quantum algorithm for solving Pell's equation. And this can be reduced to a hidden subgroup problem on the real line. And this work is due to Hallgren. And then this algorithm was further generalized to high degree number fields to solve some of the basic problems in number fields, such as finding the unit group and solving the principal ideal problem and computing the class group. And this can be viewed as HSP on R to the n, high dimensional real space. But there are some technicalities, so we actually have to update the formalism of HSP, and I'm going to call it continuous HSP. So this is work by my co-authors and myself in 14 and 16. Okay, so I want to mention this final algorithm because, as I said, this quantum algorithm can solve a problem called the principal ideal problem, which basically says you're given an ideal which is generated by a single element, and you want to find the generator for the ideal. And this turns out to be useful to break some lattice crypto. Which is a candidate for post-quantum cryptography. And I suppose you will hear some of this from Chris' lecture. Okay? All right. Now, given all these examples, one thing you might have noticed is that all the groups I have here, they're abelian. Right? Everything I've shown here, they're abelian groups. And there's no reason for us to restrict ourselves to abelian groups. We can also think about non-abelian groups and define a hidden subgroup problem on them. Okay, for example, the famous graph isomorphism problem can be reduced to a HSP problem over the symmetric group. And another example which is interesting to this audience is the unique shortest vector problem, which is an important problem in lattice crypto. This is related to HSP over the dihedral group. Okay, so when I say this, some of you might panic. Oh, does that mean we can solve the lattice problem, the unique shortest vector problem? Unfortunately, or fortunately, depending on your perspective, we don't have efficient quantum algorithm for this non-abelian HSP instances, and that's a big open question. So in contrast, pretty much we can safely say that for abelian HSP, we have efficient quantum algorithm can solve them all. But for non-abelian, we don't know, not yet. There are some instances, some non-abelian groups which we do know how to solve them, but in general, we don't have efficient quantum algorithms. Okay, all right. Okay, so given this framework, I want to, as I promised, I want to give you some intuition why the quantum algorithms actually work, for these examples we've discussed. And in fact, those algorithms can be generalized to, for us to design an algorithm for all abelian HSP. I'm oversimplifying, but that's the gist. So the key idea here is, which is the same sampling subroutine we've discussed multiple times. We call it the quantum Fourier sampling. Okay, so for a general HSP problem, the same sampling procedure will be useful as well. All right, so I'm going to just draw this algorithm, the quantum circuit, apply Hadamard, and then query your function, and then do something. What should that something be? As you might have guessed, just apply the Fourier transform over the underlying group. So we've seen this a couple of times. We have Fourier transform on Z2, which is identical to Hadamard in that simple case. And then for Simon's problem, we have multiple Hadamard. That's the Fourier transform on Z2 to the n. And then for order finding, we have Fourier transform over Z mod m, this integer group modulo m. Okay, so we just apply a Fourier transform and measure. And then this measurement outcome, there are going to be random samples from what we call the Dor group or Dor subgroup, H perp.
Sorry, for you need a different definition. I just know where.
Say it again?
This UF, what does it mean in this context?
Oh, what is, so the question is, what is UF? So again, in HSP, we have this black box function f, right? So UF is the same unitary implementation of that function f. So you have the input register x, output register y, and you compute f of x to the output register.
Before you had some XOR.
Yeah, it is the same. So maybe I can clarify. So this UF is the same unitary implementation as we've been using all the time.
How about plus in the group sense?
Yeah, I mean, that's just a convenient, like you can encode everything into binary string and translate between the different operations, if you like. Yeah, so this is the unitary implementing the function. Okay, so as I was saying, the samples here, the output measurement outcome here will be random samples from the Dor group. And with enough random samples, we can reconstruct H perp, and from there, recover the original subgroup, the hidden subgroup H. Okay, so let's put this into perspective. Let's recall in order finding. The function f here is just the modular explanation. So it's a mapping from Z to some set. So again, R is the order. Okay, so as we observed, this function modular explanation is periodic with period R. So if I plot this function very informally, so I have 0 and R minus 1. So this will be one period, so I have some function values. They are distinct on each input here. And then the same pattern will repeat itself, right, because it's periodic. So from R to, let me use a different color. So from R to 2R minus 1, I'm just going to repeat the same pattern. So this is the input function, this periodic function. And then the Fourier transform over Z. Well, from Fourier analysis, this will have a very nice pattern. It's going to be peaked at 0, 1 over R, 2 over R. So again, multiples of 1 over R, which is the dual group of RZ. Okay, now suppose we can sample from here, we get a few multiples of 1 over R. From there, we can recover R, the order we are trying to find. So this is what quantum Fourier sampling helps us to do. So I said this is oversimplifying because if we move to infinite groups, especially when we move to continuous group like R, there's going to be lots of technicality because quantum computers, we can only have finite memory and it's digital. We need to truncate and discretize the function. So that's why, for especially high-dimensional real space, when we have HSP on R to the n, we need to do something more. So that's the new continuous HSP framework. Okay, so I think this wraps up my discussion on HSP and really all these algorithms we've seen so far. Are there any questions, thoughts, or comments? Okay, maybe let me just make one remark. So we didn't talk too much about the analysis of these quantum circuits because in the crypto setting, well, oftentimes, you just need to kind of reduce some problem into one of these HSP problems and then invoke that result as a black box saying, okay, I have a quantum algorithm that can solve this HSP instance. So as long as I can reduce my problem to this instance, I'm good. Okay, so that's how we're going to be using this. You'll see some example in the exercise as well. Okay, all right. So in the last 10-ish minutes, let's move on to the final algorithm I'm going to introduce. And it has a quite different flavor. So let me move on to quantum search. So let me define, Let me define the problem first. So we're still in this black box model, right? We are given a black box function, a Boolean function from n bits to 1 bit. So again, we are assuming we have this unitary implementation for this function. And the goal here is to find some string x, a special string such that it maps to 1, if it exists. Okay, so we call this x a marked item. So we want to find such a marked item if it exists. If it doesn't, we just say, okay, it doesn't exist. Right? Now, if you think about it, classically, how many queries you need in order to solve this problem? in the worst case scenario? n-1. Or rather, you have to query everything to be certain that there's no marked item, if that's the case, right? But anyway, so classically, we basically need to query the entire domain, so that's 2 to the n. So what we're going to show next is that there is a quantum search algorithm that can reduce this cost by a quadratic factor. So we will have a quantum algorithm that can find a marked item using square root 2 to the n quantum queries. Okay, you might think this quadratic doesn't sound very significant, but if you think about it, suppose we have a key space of 256 bits. This will reduce your cost from 2 to the 256 to 2 to the 128, and that's quite an improvement. Okay, and also another nice thing about this quantum search algorithm is that you can see here we have no structure needed for the function f. It's just an arbitrary function. That's why we call this unstructured search. As opposed to in the HSP framework, all the problems, we have some nice structure for the quantum computer to take advantage of. But this algorithm is generally applicable. Okay, so let's get to Gruber's algorithm. Oh, sorry, I didn't mention. This quantum search algorithm is due to law of Gruber. And to explain this algorithm, I want to start with a geometric lemma. That has to do with reflections and rotation. So let me just explain my terminology. Okay, so on this 2D plane, suppose I have a line here, L, and I have a vector V. So I want to do the reflection about this line, so that means I'm going to take the mirror image of V, about this line L, so that gives me V perp. So this is a reflection about the line L. And another operation, simple operation, is rotation on the same 2D plane, right? So I have a vector V here. I want to rotate it by some angle theta. So that's a rotation by theta. I end up with V prime here. Really two simple geometric operations. But what's interesting is, suppose let's consider two lines here, L1 and L2. And then consider a vector starting here, V. So I want to reflect V about L1 and then followed by a reflection about L2. So let's see what we get. Exactly. So reflecting about L1, we come to V prime here, and then reflecting about L2 will be, I don't know my drawing if it's that precise, but somewhere here, V double prime. Okay? And you might have observed the net effect is going to be a rotation. And by how much? How much is this? Twice the angle between L1 and L2, exactly. So if I call the the angle between L1 and L2 to be theta, then this reflection L1 and then L2 is equivalent to rotating I guess, counterclockwise by 2 theta. Okay, so if you're not convinced, you can verify it offline. And why is this interesting? Well, we'll see. Groover's algorithm is basically 2 reflections, which gives us a rotation. And this rotation will bring us to some nice state, which will recover some marked item if it exists. Okay, so let me introduce Groover's algorithm in this quantum circuit. So we initialize 0 to the n, apply Hadamard, and then we're going to iterate on the operator, I call it Groover's operator, denoted by G. So we're going to repeat this a bunch of times. And we'll figure out this number in just a moment. And finally, we make a measurement, and this will give us the marked item, if it exists. Well, with high probability, I should say. Okay, so before defining this G, I want to show this, again, using this geometric picture. And to do that, let me introduce a few notations. So let me call the state here H after the Hadamard, and we all know what this looks like. It's just a uniform superposition over all n-base strings. So again, capital N is 2 to the n. Okay? And then let me define a state A, which is what I call X star. So this X star is a marked item. And let's assume, for simplicity for now, there's just a unique marked item in my function, X star. So my A state is just going to be the computational basis state X star. And B, another state, is going to be the uniform superposition over everything else other than X star. So all those unmarked items. Okay, so let me draw this picture. So imagine this 2-dimensional plane spanned by A and B. So let me write B here, down here. So B is kind of the bad state, right? It contains no marked item. And A here, that's the nice one. It contains this marked item. And the initial state, ket H, sits somewhere here. It's very close to B, because in the beginning, the overlap between H and B is huge, right? Because most of the components, they are unmarked. So this Groover operator, what it does is it's 2 reflections. First, it's a reflection of H about B, and then by H itself. Okay? And from the geometric lemma we just introduced, what would be the effect of these 2 reflections? It's going to be a rotation. And by how much? If we call this theta, so if the angle between H and B is theta, then this will be 2 theta, right? And we can actually figure out what theta is. Theta is just the arc sine of 1 over square root n, because 1 over square root n is the inner product, or the overlap between H and B. And since n is big, let's imagine n is big, then this is approximately 1 over square root n. Okay, so this means in Gruber's algorithm, we're keep rotating by 2 theta, and we're marching towards this nice state. Okay, and again, our goal is to kind of reach somewhere close to A. So then when we measure, we will be very likely to measure X star. That's what we want.
Sorry, can you get the arc cosine?
What's that?
That's the arc cosine, right? What is the cosine?
It should be the sine, right? Anyway, I mean, the sine theta will be 1 over the square root of n. I mean, intuitively, it has to be small. Okay? So we'll keep rotating by 2 theta every time, and suppose we rotate k times in total, and our goal is to hit this vertical line. So let's say, eventually, we would love to hit the vertical line, so that means after k times, this better be, well, I shouldn't say equal, but close to pi over 2. And that tells us roughly how large k needs to be. Well, by simple algebra, that's going to be pi over 4 theta, and since theta is roughly 1 over square root of 10, so we get something like big O of square root of 10. And that's Gruber's algorithm. Okay, so I didn't talk about how to actually implement these 2 reflections in this quantum algorithm. And I think you'll hear more about this from a future lecture by Fermi. He will talk about quantum rewinding, which in essence, this view will be very helpful, I think. Okay, so, okay, I should probably wrap up. So let me just make a few remarks on quantum search, and we can all go for lunch. So in this analysis I give you, we're assuming there's a unique market item, but in fact, this generalizes to multiple market items. And there's also a finer complexity, which says if I make Q queries with A marked items in this function, then I can find one with success probability proportional to A times Q squared over the search space. And this turns out to be optimal. That's a result proven by the paper BBBV. Actually, that was proven before Gruber found out this algorithm. Okay, so this search algorithm also has lots of extensions and applications. You can use it combined with phase estimation to do quantum counting. And it also can be generalized to a procedure called amplitude amplification. Basically, you can boost up any subroutine with success probability P using, instead of 1 over P iterations classically, you can do it in 1 over squared P iterations. So that's another quadratic speedup. And this is also kind of the starting point for a more general framework called quantum walks, at least some version of it. Okay, with that said, I think I should stop here, and I'm happy to take questions offline. But otherwise, enjoy lunch, and we'll resume in, I don't remember the time, you can look at the schedule. Cool, thank you.